is a no. Right. Look, and there's Jessica LaRousse and Jordan Ross. See, we have more people. That's the thing about online, right? You sneak in, there's no loud door closing behind you. There they are. Okay. So, what we're going to be talking about today is chemistry. So, the reason that we need to discuss chemistry is that, remember when we were looking at the organization of the body, we said that there was this kind of complexity of the body that starts with very, very small things that lead to bigger and bigger and more complex things. And so, ultimately, what we're working our way up to is looking at organ systems of the body. And our first one, like we saw like with the lecture schedule, is going to be integumentary system, and skeletal system, and muscular, nervous, and on the way, right? But we have to work our way up to that. And one of the other things that we saw in terms of that organization of the body is that each of the higher levels are made up of smaller components. And so when we talk about an organ system, it's made up of a lot of different organs that work together for a particular function. And those organs are made up of tissues, and those tissues are made up of cells, and those cells are made up of different molecules and chemicals. So we need to understand at least kind of a basic understanding of chemistry, because that's what then builds to make the things that we're going to learn about next. Okay? So let us do that. All right, so we start with some definitions because, again, we're going to be using particular vocabulary, so we need to know what they mean by it or what we might mean by it when we use it. So we start out with matter. And so matter, it's not like this matters because it's going to be on the exam. This definition of matter has to do with anything that has weight and takes up space. Now, when we think about it, right, we can say, well, that's easy for things like this stool, right? I can feel that it has weight. It obviously takes up space. I can't walk straight through it, etc. But that also translates down to a very, very small, beyond microscopic level, right? So things that are reacting, chemicals and elements and ions that are reacting, even though we don't feel them and we don't see them, they exist and they take up space, and they have a weight. Now, this is going to be a molecular weight, so it's very, very small, but it still counts. And so they are what make up these things that we would call matter. So from a very small scale to a very big scale. And chemistry, and so Jordan says, wouldn't we want to say mass instead of weight? Yes, definitely so. So what Jordan's talking about there is that when we are talking about things that are here, associated with us on Earth, due to the effect of gravity, then everything that has mass has weight because the effect of gravity pulls on that and gives it a weight, right? If you go up away from a body that has a gravitational pull, that's when you start talking about mass instead. And so for our intensive purposes, weight and mass are basically the same, but that's a good technical distinction between the two. So with chemistry, what we're talking about there is we're talking about how these different types of matter will interact with each other and change in terms of big things and small things and how we can hook things together and how we can take them apart, etc. So that's what chemistry is, how the composition, what makes things up, and how that changes through time. And then we can even think about an example in the body for that is like with the digestive system, right? You're taking in these large, bits of things, and your body is working to break them down physically and chemically down to small enough molecules that can then be absorbed across your intestinal wall, can float around in the bloodstream, and be utilized by these microscopic cells for their particular needs as living things. Okay? Okay, so starting at the smallest level, at least in terms of what we would call elements, these are individual units here that have been numbered to about 111. Now, there are more. Unfortunately, in this room, we don't have a periodic table. There are other elements that there's constant research going on where they can have elements that exist only for like a nanosecond and then fall apart again. but generally we're talking about these that have a sustained, if you will, quote-unquote life, right? It's not living, but they will hang around for substantial periods of time. There's about 111 of those, and the body has about 20. And when we look at the different elements, the ones that we're mostly made of are these, which is oxygen, that's the O, carbon, that's the C, hydrogen, which is the H, and nitrogen, which is the N. Okay? And the molecules that make us up, that make up our cells, etc., are a lot of different combinations of mainly those four, oxygen, carbon, hydrogen, and nitrogen, but also there's a number of other ones that may occur in smaller amounts that can make different types of molecules, that can make the difference between a complex carbohydrate or a simple carbohydrate like sugar or something like that, can make the difference between proteins and nucleic acids, etc. Okay? So those molecules are where we have elements that we stuck together in various ways, and it depends on how many elements there are and how they're attached to each other and what elements they are as to what that molecule is and what it can do. Okay? So these elements are basically the smallest complete units are these individual atoms. Okay? Now we will find that there is a level below that that we call subatomic particles as well, but these are the smallest as it says that they're complete units. And so they are going to make up the building blocks, like Legos, the building blocks that we can then create larger molecules, etc. Right? So if you look in your box of Legos, you've got different shaped pieces, you've got different colored pieces. Those are much like the individual atoms. Okay? Now you could take a hammer and you could break that individual Lego into smaller pieces, but it wouldn't retain its original characteristics anymore, right? It used to be a six-piece block or whatever, you know, and if you hammer it, now it's not that thing anymore. You've broken it apart. And so the elements or the atoms are kind of like the individual blocks or Lego blocks. Now, like we said, the individual elements get their characteristics, what makes oxygen different from carbon, etc., besides the letter that we use. Well, those individual atoms are made up of different what we call subatomic particles. So subatomic particles, if we look at that word, so a subatomic particle, subatomic, is like that. Let me make that a little bit bigger for us. Okay? Subatomic particles are going to be those that make up the atom. S-U-B-A, oh, now it's not clicked in there, sorry. Like that, okay? So subatomic particles are going to make up the atoms, and the subatomic particles are protons, neutrons, and electrons, okay? Now the interesting thing about the atom, the way that the kind of physicists and stuff like that understand it is that these three different subatomic particles make up an atom, and they're located in different places of the atom, and a particular atom will have different ratios or different numbers of these different subatomic particles. So the protons, if we look at that term, pro usually means positive, right? So if you are for something, you're pro for it. And so the protons actually have a positive charge to them. The neutrons, if you look at that one, a neutron makes you think of neutral, right? Doesn't have a charge. And then the electrons are negatively charged. And so these are the three different subatomic particles. The protons and the neutrons exist in what's called the nucleus of the atom. Now it's kind of funny because when we get to the cell, we'll find that there's a nucleus of a cell as well, but an individual atom of nitrogen or something like that has what they would call a dense core to it where most of our protons and neutrons are going to be located. The electrons are a little bit different. They are kind of flying around the nucleus instead, as far as they understand it. Okay? So this is a diagram representing three different atoms. Okay? So here we see hydrogen, helium, and lithium. And like we said, to tell the difference between these different atoms or elements, we look at the number of protons, neutrons, and electrons. So you can see the protons are going to have the positive charge shown in red there. The neutrons are going to have a little zero in them because they don't have a charge. and the electrons are going to be these little blue ones with a little minus sign on them. Okay? And we can see now, besides the word being different, we can see how these individual atoms are a little bit different, right? Hydrogen has a proton, has no neutrons, and has 1 electron. Okay? An individual atom of helium has 2 neutrons, 2 protons, and 2 electrons. Okay? So they're each a little bit different. Now you'll notice that in these basic atoms, we have the same number of protons, which are positively charged, as electrons, which are negatively charged. And that keeps everything in balance. Okay? The number of neutrons with the 0 there varies depending on what we see for the individual atom as well. And so, for instance, hydrogen has no neutrons. Helium has 2. So when we look at these, the number of protons that you have determines what's called the atomic number. These are characteristics. Each element has a letter that designates it, like H and O and C. Okay? It also has an atomic number, which tells you the number of protons it has. So usually it has a little subscript to it. And then there's a number of neutrons in there, which the neutrons plus the protons, if you count those up, it gives you the atomic weight. Because we said that things that are made up of matter have a weight or mass, and so even those individual neutrons and protons, etc., have mass, and so you can weigh them. So the weight of helium versus hydrogen comes from the number of these subatomic particles like that. Now when we look at the diagram here, they try to give you a relative, if you will, size of the balls that compares to the mass or the weight of these subatomic particles. So the protons and the neutrons have the most mass. Each one is about what we call Dalton. Dalton is the unit that we use for these subatomic particles. The electrons themselves are much, much smaller. And their mass, while they do have mass, is much smaller compared to the protons and neutrons. So when we're calculating the atomic weight of an individual atom, you almost ignore the electrons. You kind of round off. You say, okay, if I count out the protons and the neutrons, that's most of the mass or weight anyway. So we'll just kind of round off there and kind of forget about the individual electrons. Okay, so let's take an example here. So this is sodium. This is an individual atom of sodium. Sodium, in its nucleus, it has 11 protons, 12 neutrons, and then it's going to have, to balance out the bounce off the 11 protons, it's going to have 11 electrons going around here. Okay? So in terms of atomic number, right, if we look back here, it says protons determine the atomic number. We saw that we have 11 protons, so the atomic number for sodium is 11. Now the atomic weight we said it was the number of protons plus the number of neutrons, and we kind of ignore the number of electrons. So the atomic weight is 23. Okay? Now technically it's like 23.00554, whatever, okay, due to the presence of those electrons, but we can kind of round it off to a whole number like that by adding the protons and the neutrons. Okay? So each atom has a unique atomic number, a unique atomic weight. Now these electrons that we were talking about out here, like we said, they're not located in the nucleus. They're actually kind of flying around, much like you see, like, you know, the moon encircling the Earth and things like that. They are also in different orbits like that. And so the number of electrons that you have, they will be going around in these different orbits. And each of those rings that you see there is a different orbit. Each one only has a certain amount of room for a number of electrons. Like the first one can only hold 2, so if you have more than 2 electrons, then they go to the second orbit, and there's 8 out in that one, and you go out to the third one and stuff like that. Okay? You ever see that? There's a cartoon called Jimmy Neutron, right? And they have the symbol, right? It shows this little ball in the center, and it shows these things going around like that. That's that. Okay? So it's showing you an individual atom with the electrons going around like that. Okay? Okay. So, do we have questions on atoms? That's the first step. Atoms or elements. Yeah?
You said the electron costs taken out of the protons.
Mm-hmm. In a regular atom. We're about to just go into, when we take atoms, how do we stick them together? And we'll find that there are cases where you can actually lose an atom, right? It's like leaning around, or you can gain you can lose an electron, you can gain an electron. So the number of electrons can actually change. The number of protons and neutrons always the same for an individual atom or element. Yeah?
For cells, we only have 2 electrons.
Yeah.
And the second,
So it can only have 8. The third one is also 8, and then you kind of go on from there. So like if you were actually taking, right, you can take a whole chemistry class where you just study this stuff. And in that case, what you do is you actually have to calculate and diagram out. They say, okay, for chlorine, diagram out where all the electrons are and put them in the right shells and stuff like that. And so then you would have to know 2 in the first one, 8, 8, 8. Here you don't. But, I mean, it's kind of interesting to be able to, at least it was to me, to learn how you map out all these subatomic particles and think of them kind of spinning around and interacting and things. So, okay. So the next part of the process then is to look at how we stick these things together, right? So we go from individual atoms, we need to stick them together to make molecules. So how do we do that? So we create what are called bonds between the molecules, or I'm saying between the atoms. And so that's, you know, kind of like people getting married or something like that, right? They form a bond and they stay together. So we have different types of bonds, and maybe, like marriages as well, there are different strengths of that bond, stronger or weaker or whatever. And so the ways that, different examples of ways that we can bond atoms together are these. So one is called an ionic bond. And this is what we were just talking about, where an individual atom may gain or lose an electron. So changes in local energy and things like that can cause these charged particles to be removed, like lost or gained. And so what we find is, when that happens, then the individual atom, or what we call now an ion, see the term ion there, an individual ion is kind of not quite as stable as it used to be. These atoms like to feel complete, if you will, all right? So what that means is what Darren was talking about before. For those orbits, they like to have nice full orbits. So they'd like to have, if in the first orbit, they like to have 2. If they have 1, not totally full. They don't feel complete. If they have more than the 2, then they like to have a totally full second orbit, etc. Okay? If they gain or lose an electron, now they don't feel complete anymore. So again, much like some people in relationships, they don't feel complete, and so they go to get together with another individual, and then they feel complete, right? So that, to a certain extent, is what happens with ionic bonds. In these cases, we've got on this side a sodium ion that has actually lost an electron. Now that sodium ion, notice that red plus over to the left of it, when it loses an electron is negatively charged. So when you lose a negatively charged thing, you become more positive. It's kind of like in your life, right? So if you have all these negative things in your life and you start getting rid of them, all of a sudden you feel more positive about your life, right? So if an atom loses an electron, then it gets a positive charge to it. So that's the sodium ion right there. It's lost one of its electrons. On the right side, we see a chloride ion, and a chloride ion in this case has gained an extra electron. So because electrons are negatively charged, when it gains another negative thing, it becomes more negative. It has an overall negative charge to it. Okay? So what we have here is 2 separate ions, one with a positive charge and one with a negative charge. And again, like relationships, you often hear that opposites attract. Same thing in terms of what we call ionic bonds here. So if you have 2 oppositely charged ions, they will tend to associate with each other, much like magnets, right? You got a positive end to a magnet and a negative end to the magnet, and they will be attracted to each other. So this is what's called an ionic bond. They will attract to each other electrically and make, in essence, an ionic bond. Okay? If you had individual atoms, hadn't gained or lost electrons, they wouldn't have this imbalance. They wouldn't have this attraction to each other. Okay? So that's an ionic bond. And so does anybody recognize this particular molecule? It's called sodium chloride. Right, that's salt. So the salt crystals that you have in the salt shaker, that's what it's made up of. It's made up of sodium ions and chloride ions that are actually attracted to each other. there's enough of an organization to that it forms nice regular crystals like that. Okay? Now, if you take that sodium chloride and you put it into water, okay, we'll learn that the water molecule is actually a polar molecule. It, as a molecule, actually has a charge on one side of the molecule that's positive and a charge on the other side of the molecule as a whole that's negative. So what happens is you have these two ions that were originally attracted to each other. Now they get in this water party, and there's all these other attractive things there, and it pulls these individuals apart. So when you put the salt crystals into the water, it dissolves because the sodium and the chloride, which were once attracted to each other, now are straying from each other, and they separate. And so it dissolves because it goes back into ionic form. Okay? Individual ions instead. Okay. All right, so that was the first example. The second example of a type of bond that holds atoms together to make molecules is called a covalent bond. Okay? So a covalent bond is another type of bond where our individual atoms don't really feel complete on their own. Okay? Now, for our last example, we saw that there was kind of a charge on those atoms that made them ions because they had either gained or lost an electron. In their native state as an atom, they normally had like 11 different protons here, okay? 11 protons and 11 electrons to balance it out. But if it lost one of these and it only has 10 electrons, then this whole ion here has a charge to it, okay? Which makes it attracted to something else of an opposite charge. For a covalent bond, that's kind of similar. But what's happening here is, in its native state for an individual atom, it may not have all of the electrons that it likes to complete those different orbits like we were talking about before. And we said that these individual atoms, they like to feel complete. Okay? Now the first one was this idea of opposites attract, that they have an overall charge because they have gained or lost an electron. The second one here with the covalent bond is just saying in their native state, they don't have, oh, I don't have a good diagram there, they don't have the right amount of electrons to fill their outer orbit. So look here, here's a sodium atom, okay? A sodium atom naturally has 11 electrons. You can see 2 in this first orbit, a nice full 8 in the second orbit, and then it's got this 1 right there, okay? So it, in its native state, is kind of imbalanced there. Now, again, if it loses this electron, then it's an ion, and now it has an electrical charge. Opposites attract. But even in this other state here, where it has its natural last electron there, it doesn't feel complete because it's got this outer shell that is not entirely full. Okay? So what happens is, if you have a covalent bond, then what you end up having is 2 atoms that complete each other. Let me give you an example here. So look at hydrogen here, okay? Hydrogen has only 1 electron as an atom. Now we know that that first shell can hold 2. So right now it feels like half complete. If you take an individual hydrogen atom and you put it with another hydrogen atom, then what happens is they will complete each other, okay? Because each one wants to have a full shell out here. Each one wants to have 2 electrons going around in its orbit. And so what happens is, see if we can draw this out here. If you have 1 hydrogen and another hydrogen like this, I'm going to put that proton in the center here. Now it looks like eyes just looking back at you. But what happens here is if we've got 1 electron from this one and 1 electron from this one, remember that the electrons are constantly going around these orbits. So at a particular time, when these individual electrons are going around, this one may go around here, and it may end up on this orbit around this one. And for that period of time, this atom is very happy because it's got a complete orbit. It's got 2 electrons going around in that orbit, and it feels full. And then on another fraction of a second, these 2 elements may shift to this one, and now this one is happy because it's got 2, right? So in essence, by sharing those electrons, they feel, those 2 atoms feel more comfortable and form a bond called a covalent bond because they're filling their orbits with the electrons from each other. So they're sharing electrons, okay? So sharing electrons is what we're doing for a covalent bond. And there's a lot of molecules that are formed by a covalent bond, and it holds those elements together because they want to feel complete by completing their outer shells of electrons, okay? Okay, our last example of a type of bond is called a hydrogen bond. And a hydrogen bond is not necessarily a bond that would form molecules. And what we're seeing here is different water molecules represented. So you see the oxygen atom with two hydrogens attached to it. Those are covalent bonds which cause the hydrogen and the oxygen to bond to each other. They're sharing electrons. Everybody gets happier that way. And oxygen has 6 electrons in its second shell. It wants 8. If it shares the 1 from each of those hydrogens, the hydrogens are happy because at times they have 2. The oxygen is happy because at times it has 8 and it's complete. All right. So, the hydrogen bonds don't really form molecules, but what they do, like you see here where those dotted lines are, they help to organize molecules with each other. And so in this case, like when you have water molecules together, like in a fluid or something like that, they will organize with each other so that the hydrogens are kind of pointing towards the oxygens of opposite molecules. And again, that kind of has to do with the organization of the water molecule, but a weak bonding between hydrogen and other atoms can cause certain molecules, like water molecules and proteins, to organize with each other when they're closely associated. So hydrogen bonds are kind of the weakest of our 3 bonds. They don't make molecules, but they organize molecules. So like a protein that we'll learn later on, a protein is a long, complex molecule that winds back and forth and back and forth. It's made up of amino acids. The shape of that protein is very important to allow that protein to do what it needs to do. Like there's a protein in your blood cells called hemoglobin. Anybody know what hemoglobin does? So you've probably heard of it. Hemoglobin binds oxygen, okay? The only way it's able to bind oxygen is it has this little pocket where the oxygen molecule fits in. And the shape of that protein is very important so that it fits like a lock and key mechanism with the oxygen molecule, okay? Hydrogen bonds help to create that form of the protein to make sure that it fits with the oxygen molecule, okay? So that's a third type of bond of ways that we can, in this case, organize molecules with each other. So that's kind of a tour of different ways that we can make molecules, okay? So we go from atoms, individual atoms or elements, to molecules. So we're working our way up. All right. So now we've got this idea of a molecule. So a molecule is where we have 2 or more atoms that are bonded together in some way. There's another term that's associated with molecules that's called a compound. When you see the word compound, compound refers to the fact that we have a molecule that has 2 or more elements to it. So if we look at the different molecules down at the bottom of this slide, you see hydrogen. See that H2? That's 2 hydrogen atoms linked together, okay? That is hydrogen gas. The next one, right next to it, is oxygen gas. You can see how they're linked together. Those 2 would be known as molecules, but only until you get to the ones on the right would you call those compounds, where you have 2 or more different elements linked together, okay? All right. The other thing that we have to talk about when we're getting up to molecules here is the difference between what's called a molecular formula and a structural formula. Now, you won't have to write these out and kind of figure that out. You would do that in a chemistry class. But what you see here is 2 different ways of writing out or displaying chemistry. And so a molecular formula is basically more like a recipe here. Okay? So if you have a recipe to make something, it says, oh, okay, I need 2 cups of sugar, I need 2 cups of flour, and I need a teaspoon of baking soda, etc. Right? It tells you what and how much goes into that particular recipe. So the molecular formula is like that. So H2 tells me that there's 2 hydrogens in that molecule of hydrogen gas. H2O tells me there's 2 hydrogens and then 1 oxygen. Okay? If there's only one of a particular element, they don't even bother with the number. Technically, you could have a little 1 subscript there next to the oxygen, but they don't bother with that. Okay? If there's more than 1 element, then they give you the number down there. So you can get, like, glucose is like C6H12O6, and it tells you how many of each of those elements go into it. That's one part of it. Structural formulas give you even more details. They tell you exactly where those things link together in order to make that particular molecule. And that's important because you can have the same recipe, right? But if you mix it together in different ways, you can get different things, right? Like if you had the same elements, but you cooked it in a different way or you blended them in a different way, you can come out with a different product, okay? Okay. Now the next step of this process in building and things like that is we talked about different ways that we can hold the elements together, but what are these chemical reactions that can cause them to come together and fall apart? So we've got different terms for that, and we'll see this when we're talking about, when we're talking about muscle and how you make muscle, when we're talking about digestive system and how you break things down, okay? So this will come into play later on. So chemical reactions. Synthesis reactions, like you see on the first line there, are where we take two smaller components and we knit them together and make something bigger, okay? So you're synthesizing it, you're creating in that case. So that's just a generic example, right? So like if we had two individual hydrogen atoms and an oxygen atom and we bonded them together, we would then have H2O, the water molecule, okay? Decomposition reactions, that should be kind of self-explanatory, right? Probably right now in your refrigerator, you've got a decomposition reaction going on, something that's kind of falling apart and getting moldy and stuff like that, right? It's where you started out with something big, and now it's being broken down into its individual building blocks. Decomposition reactions are something that's certainly going on in your digestive system, taking something big, breaking it down further and further into building blocks. Exchange reactions. Exchange reactions sometimes happen in the body. If you look at that, this is like some sort of a swingers party right here, right? So what you have here is you showed up as two couples, A and B and C and D, and you left with different partners, right? So you exchanged them. We didn't synthesize anything new. It didn't get bigger. It didn't get smaller. Everybody's the same size, but partners were exchanged, okay? The last one that we have listed there is probably the most relevant for what's going on in the body, and it's called the reversible reaction. And it's got kind of a two-ended arrow there. And what that is saying is that depending on the body's needs and what's going on, we might need to synthesize and build things up, and then maybe later on we actually have to break it down and go down to those building blocks again and use them for something else. Same thing, if we use the Lego example, right? So you start out with your building blocks, you spend some time building something up, etc. Now you used all your pieces to build that. You want to build something else? You've got to take it apart, and then you can use those building blocks to build something else. That's what the cells are doing on a regular basis. They're utilizing the building blocks. They need more of them from the nutrients you take in, but they're also utilizing those to build and decompose things. And they'll go back and forth, okay, depending on the bodily needs. So reversible reactions, it all depends on what's going on in the body. The last thing that we see there is that these are all chemical reactions. And they generally happen pretty fast, but much like when you're, again, using Legos, the synthesis reactions usually require energy. So just like when you're building something, it takes energy for you to actually put those blocks together, and it takes time and energy to do so. Meanwhile, in a decomposition reaction, that doesn't take too much, right? If your little brother or sister comes up and goes, pink, and knocks over whatever you built, it falls apart pretty easily. And so the decomposition reactions usually release energy. The synthesis reactions usually require energy, and we'll talk about that later on. A catalyst is a certain type of molecule, we usually call it an enzyme, that affects the reaction speed. So if we're synthesizing things, that's going to take energy, and it's going to take a while to do it. If you have a catalyst there helping you, a separate molecule, it's like a helper molecule that allows that chemical reaction to occur easier and faster. And so we'll talk about different types of enzymes and catalysts, particularly when we get to digestive system. Let me see. So an enzyme, E-N-Z-Y-M-E, is like that. An enzyme is actually a catalyst. It's a biological catalyst that helps these reactions occur. Okay. So now we've worked our way up to molecules. Questions on molecules and chemical reactions and things? All right. All right. So now what we need to do is look a bit at different types of reactions, different types of molecules and reactions that are important to us in the human body. Okay? So the first thing that we're going to start with are these things that are called acids and bases. And so there are lots of different types of ions in the body. We said that if we have an atom and it loses an electron or it gains an electron, it becomes an ion and it has a charge to it. Okay? Now, if you are talking about substances like we talked about before, like sodium chloride, and you put it in water and it automatically dissociates or falls apart into ions, that is what we call an electrolyte. Okay? So electrolytes are commonly called salts. And so if you take a salt, when it's in its kind of molecular form, it generally forms a crystal. And if you put it into water, it dissolves. It falls into its individual ions. Okay? So electrolytes are something that you can sometimes hear, right? Have you guys heard of electrolytes? Where do you find electrolytes? Gatorade. Right, Gatorade, right? So they say that the Gatorade and Powerade and stuff like that much better for you than just water because it's got electrolytes in there. And you're looking at that and going, I don't know, it's like pixie dust or something like that. Is that what gives it the neon color? Is that? Then I got to drink that? So, and then you see those Gatorade commercials, you see it like coming out your pores. You're like, oh, I don't want that. I don't want blue coming out my pores. So from this, we learned that electrolytes are basically just salt, right? So that's what they're putting in there, right? It's got water and it's got sugar, actually, and salt. So they've taken a pinch of salt in there and they're like, ooh, it has electrolytes. It's not that it's not important. It's just that they make it sound like it's something much more special than it is. And certainly, right, you think about working out, you lose fluid and you lose salt, right? The salt is, the sweat is quite salty, so you need to replenish that. But that's what we define as electrolytes. So if you have electrolytes that fall apart into ions, there are a couple subcategories of electrolytes that are important. If you have an electrolyte that when it falls apart, it releases hydrogen ions, then that's what we call an acid. Okay? So here is an example of a common acid. So HCl. Okay? So that's hydrochloric acid there. It's one hydrogen and one chloride that's actually attached to each other. So that's hydrochloric acid held together by an ionic bond. And so what happens is that will tend to fall apart when you put it in water, and it will release one hydrogen ion and one chloride ion. So by definition, yes, it's an electrolyte. But second thing is it's also an acid. And you guys know that acids can burn and stuff like that. What can happen is those free hydrogens will tend to react with other molecules, and it may cause those molecules to break down. And if they break down, that's kind of where some of the burns that you think of come from, chemical burns. And so acids are electrolytes that release hydrogen ions. Now on the flip side of the coin, there are these things that are called bases. These are also called alkalines. So these bases actually are electrolytes that when needed, they can actually bind up hydrogen ions. When they fall apart, they release things that can, later on, bind the free hydrogen. So an acid releases a free hydrogen, so you have hydrogen ions that are floating around. Okay? If you have a substance that binds up hydrogen into a molecule again, that's what we define as a base. Okay? So if we have an acid and a base together, it actually ends up neutralizing each other. So let's take a look. So if we have, let's say, hydrochloric acid plus sodium hydroxide, okay, sodium hydroxide is a base. What we get is H2O plus NaCl. Okay? So hydrochloric acid is something that releases hydrogen. Sodium hydroxide will bind up hydrogen. And so when you combine those together, when those ions fall apart, they will bind up. And if you look at the second part of the reaction, water and salt, you don't have to be afraid of that, right? That's not going to burn you or anything like that. So the base has basically bound up the free hydrogen and neutralized it. So Jessica online was saying, what are the ions called that combine with the hydrogen ions? Do they have a name? So the ions particularly, like I said, the electrolytes that release hydrogen are going to be called acids. The electrolyte, the substance, the molecule that can bind up hydrogen when it falls apart is called a base. But the individual ions can be different. So the OH that we have right there is called a hydroxyl group. But it's only one example of something that can bind up hydrogen. So that's more kind of specific chemistry than what we need to know. All right, so the reason that we bring up pH is that when we were talking about homeostasis, we said that in order to maintain our internal condition, there's lots of different things that our body systems are working to control, like temperature and nutrient levels and waste product levels and oxygen levels and stuff like that. We want to make sure that we have enough of those things and not too much. pH, which is basically how acidic a particular solution is very tightly controlled in the body. So for instance, your blood has a pH typically of about 7.4, okay? 7.4, the pH scale goes from 0 to 14. So halfway between 0 and 14 is 7. So totally neutral, like water, is at pH 7, because it's got one hydroxyl group, an OH, and it's got one hydrogen, so it's got exactly one thing to bind hydrogen and one thing that is hydrogen, so it's exactly balanced, okay? So when you have water, that's exactly pH 7. Our blood is pH 7.4. The high numbers on the pH scale are more basic, and the low numbers on the pH scale are more acidic. Okay, so we see pH 0 down there, acidic. You see here 14 way up there. Okay, neutral right here in the center. Our blood is slightly basic. You can see right here, 7.4. If it goes to like 7.35 or 7.45, if it gets out of that range, all of a sudden a lot of systems start shutting down. It's that tightly controlled. If you go below 7.35, it's called acidosis. If you get above 7.45, it's called alkalosis. And it has a big systemic effect because the blood routes out to everything. So if you've got a problem with the blood, lots of different things are affected. Yeah? So pH, you can think of it as, it's not technically this, but you can think of pH kind of like percent hydrogen, okay? So the more free hydrogen ions you have floating around in a fluid, the more acidic it is. The lower the number on the pH scale. So it's the concentration of free hydrogen ions in the solution. It's not really percent, but you can kind of think of it that way in terms of the P and the H, okay? Okay, so if you look at this table, it's kind of interesting to look at some of these substances and see how acidic or basic they are. Sodium bicarbonate that you have in the house is a basic substance. Milk is somewhat acidic. If you go to kind of tangier things, like different types of juices, they get more and more acidic. So like citric juices and stuff like that, orange juice and things like that, but that tang comes from the free hydrogen that's in there. The tangier it is, the more acidic it is. So lemon juice, really tangy, very, very acidic. Like on the order of 1, pH 1 and stuff like that. It's not going to burn you or anything, but like if you got an open cup or something and you put it on there, you can definitely feel the acidic nature of it. So acidic things, basic things, okay? So there's lots of different examples of that. And your body will tightly control that. Okay, so when we start looking at, we're trying to graduate up to the cellular level, okay? So when we start looking at what makes up our cells, we said that with the atoms of the atoms, like 111 common ones, okay? There's 20 that make up most of your body, and 4 of those, carbon, oxygen, hydrogen, and nitrogen, are the main ones that make up your different molecules that make up your cells, etc. So when we look at the common molecules that make you up, there's 2 categories of them. One is called organic, and the other one is called inorganic. Okay? So organic molecules are those that contain carbon. They have to contain carbon. Now they usually contain hydrogen. They often usually contain oxygen as well, but they have to contain carbon. Okay? That is the definition of being organic. Inorganic molecules are basically all the rest. Okay? So when we look at it, the organic molecules are going to be more similar to the molecules that are making up you. Whereas the inorganic ones, they're not bad, they're just molecules that are different from the normal molecules that make up your cell. Okay? So a lot of people hear about organic and inorganic when they're thinking about, oh, okay, like foods and stuff like that, right? You go to the produce department, like organic vegetables, this is supposed to be better for me, I don't know why, right? That's because when those different vegetables are being raised or farmed, they don't use pesticides and things like that. They are raised in a way that is more similar to natural ways, which are more similar to your body, so it's less of a quote-unquote stress on your body. You're not introducing these extra chemicals that are very dissimilar from your body. Okay? So, but you don't want to think of inorganic things as being bad. If you look at these lists of inorganic things, right? Water, H2O, no carbon in it. It's not bad though. It's not a poison in it. You have to have water. You're mostly made up of water. Okay? This is just a way of categorizing these major molecules that make up organic and inorganic. So the last thing we're going to do is look at some major organic molecules of the body. Because we said that these are going to be the molecules that are the building blocks for you. So a lot of these, luckily, because of diets and things like that, a lot of these people have heard of, whereas once upon a time, maybe when you were teaching this class 20 years ago, everybody's like, I don't know, what's the protein, what's the carbohydrate, I don't get that. Now, like nutrient information, fad diets and stuff like that, they're like, oh, okay, yeah, you totally have to know the protein content of that food item and the carbohydrate and fat content, etc. Okay, so at least it gives you guys a leg up on it. So, carbohydrates. Carbohydrates are commonly used in the body for energy and structure. Okay, so they can be used to build things on a cellular level, and they can be used for energy. And some common examples, right, you hear of complex carbohydrates, and then you hear of like simple carbohydrates, like simple sugars and stuff like that. So sugars are certainly used for energy. It's not they're a bad thing, right? You get all these diets and say, oh, carbohydrates are evil. They're not evil. The idea with this is that you have to be in balance. And with diets and everything, and with living, it's about input and output, right? If your input and your output are in balance, then everything's good. When one of those gets off, now you're at imbalance, right? And we just find that a lot of things that we eat end up being very high in carbohydrates. So you usually have more input for that than you necessarily need. Okay? So energy input is like a banking account, right? So if you have a lot of deposits, right, and not a lot of withdrawals, then you get savings, right? Right? It stays there. You got to keep it somewhere. You're depositing where they're going to go. It goes into savings. So if you want to reverse that trend, what do? You cut down on the deposits, increase the energy withdrawals, and then what do you got to do? You're checking that balance down. Oh, I got to take it from savings in order to balance that out. So that's kind of how that works in terms of the balance. All right. But that being said, and having you guys think about your individual energy balances and things like that, we are at the end of our time period together. So what we're going to do, we're very close to the end of chapter 2. We're just going to go through these different organic molecules and talk about what they do in the body and what they're made of, etc. And then we'll be able to move up to the cellular level. So next time, make sure you bring the lecture notes for chapter 3 for cell. So we're going to move up to that level. Once we get past cell, then we're on our way up to tissues and things and organ systems, etc. So we're up to where you're thinking you're going to be originally. All right, so we'll see you then.